So welcome to the final part of the IGCSE Astrophysics Unit, and the final part is Cosmology. And as you can see at the slide in the top line, Cosmology is a branch of physics concerned with the origin and development of the universe. So what that means is where the universe came from and what's going to happen to the universe in the future. And the theory that is generally widely accepted is the Big Bang theory, and it was suggested in the 1920s, nearly 100 years ago, that 13.8 billion years ago the whole universe was a very small, extremely hot and dense region, and from that point the whole universe expanded outwards to what exists today. And so it's like an explosion that has been carrying on for 13.8 billion years. And we know that the universe is still expanding today at an increasing rate. But what we don't know is what will happen. Will it carry on expanding? Will it just stay at the same size? And or will it collapse in on itself? Now, according to our theory, the universe should collapse back in on itself because gravity should pull it back in. But it's not happening, and that's because of something called dark matter, which you might have heard of, and it's well beyond this specification, but I will try and mention that later on in the unit. So just a way of modelling this, if you imagine on the left hand side you've got a blue region which represents the universe, and these yellow dots are galaxies, and as the universe expanded the galaxies get further apart. So there's still the same number of galaxies, but they're just getting further and further apart. And you might be asking yourself, well, where is the evidence? And we do have quite a lot of evidence actually that this actually did happen and is happening now. And so what the main purpose of this unit is to explore that evidence. So what evidence do we have for the Big Bang theory? And what we're going to do is look at this first piece of evidence, and there's quite a lot of physics here, and we're going to watch a video first of all, and you need to have your speakers on. Now the video you're going to watch is of a car with its horn on, and the car is coming towards the person holding the camera, and then the car will move away from the person who's holding the camera. So you should have watched that video 3 times of a car coming towards and moving away from an observer, and you would have noticed the sound getting louder as it got closer to the observer. But also you might have noticed, it's quite a subtle effect, but the note also the note from the horn gets higher pitched as it gets closer to the observer, and then as it moves away from the observer it gets lower pitched, and that's called the Doppler effect. The fact that sound changes its pitch, gets higher as it's moving towards you and lower as it's moving away from you, we give that a name and it's called the Doppler effect. And basically what is happening is, imagine this case, you've got an ambulance with its siren on, and it's coming towards you. You'll hear another sound again when I go through this. So the sound waves are being emitted in all directions. And you might have heard it there as that sound of the ambulance siren recording was playing, that it got higher pitched and then it got lower pitched as the ambulance moved away from the observer. And basically what's happening is that as the sound moves towards you, all the sound waves get squashed together, and as the sound moves away from you, the sound waves get stretched out and they get further apart. So if you're listening to an ambulance coming towards you, it sounds higher pitched, and if you're listening to an ambulance siren moving away from you, it sounds lower pitched. Now, we will go, if you're in year 9, we will go into this in a bit more detail in year 10, because there's a lot of sound theory that we need to cover to understand this properly. But the whole point is, sound is a wave, and if sound behaves like this, then other waves should behave like that too. And light actually behaves in a similar sort of way. And the fact that light behaves like in this way is going to give us evidence for the Big Bang theory. So how is the Doppler effect related to light? Well, what you see here at the top is a spectrum of white light. So when we look at white light through a device called a spectrometer, the spectrometer breaks it down into the colours it's made of. So white light is made of red, orange, yellow, green, blue, indigo and violet. And we can see those colours here, and violet are short waves and red has a longer wavelength. But when we look at the white light from the sun, we not only see that spectrum, we see the violet, red, orange, yellow, green, blue, indigo, violet, but we see these dark lines as well. So there's a dark line here, and there's other dark lines. I'll just point to them there. Now, the sun is emitting white light, but some of the colours or some of the wavelengths get absorbed by the outer layers of the sun, and the outer layer of the sun is called the corona, and that absorbs some of the colours. So this bit gets absorbed by the corona, this bit gets absorbed, that gets absorbed, that gets absorbed, and that gets absorbed, and so does this bit here. And we call this, whereas this is a spectrum, this is called an absorption spectrum, because some of the bits of colour or some of the wavelengths have been absorbed by the outer layer of the sun or the corona. Now what gets interesting is when we compare the light from the sun to the light from a distant galaxy. And here, the top diagram, you can see the spectrum of light, white light from the sun that has been analysed through a spectrometer, and you get the 7 colours, and you get these dark lines that have been absorbed by the corona, which is the outer layer of the sun. But what's interesting is when we look at the white light from a distant galaxy, we still get these dark lines, but they all appear to have moved by the same amount, and they all have moved towards the red end. Now, what does this all mean? And that's what we're going to explore in the next slide. Now, it was Sir Edwin Hubble who first investigated the light from different galaxies, and he had a ground-based telescope, and basically he was looking at galaxies like this or galaxy here, and he looked at the spectrum of light from different galaxies. And just as an aside, in recognition of the work that he did, 30 years ago we put the Hubble telescope into space, which gave us even better and clearer images of the galaxy. But here are his results, and this is the spectrum of the white light from the sun, and you can see these dark lines. This is the spectrum for a nearby galaxy, this is the spectrum of light for a distant galaxy, and this is the spectrum for an even further galaxy, and you can see that all the lines have been moved over to the red side, and we call this red shift. And this is similar to what sound does when it moves away from us. So when you were listening to the ambulance siren or the horn, as the sound moves away from you, it got lower pitched. And the same is happening to light, that as the galaxy's moving away from us, the dark lines are shifted to the red side, and the greater the shift, the faster they are moving away from us. So the fact that Hubble looked at all these galaxies and they all showed a red shift means that everything is moving away from us. And if all the galaxies are moving away from us, then if we pressed rewind and went back in time, then they all must have been together in one place. So what this evidence shows here is that the universe is expanding. Whatever galaxy he looked at, the vast majority of them showed a redshift, which means that they are moving away from us. Now, if you're in year 9, don't worry too much if you haven't got a grasp of this, because we haven't covered sound yet. But all you need to understand is that the fact that when we have these dark lines, when we look at nearby galaxies or distant galaxies, the dark lines have shifted over to the red side, and we call that redshift. And the bigger the redshift, it means that the galaxy is moving faster. So it tells us two things: the galaxy's further away and the galaxy's moving faster. And if all the galaxies are showing a redshift, if we pressed rewind and we could go back in time, then everything would start from the same place. And this is the major piece of evidence for the Big Bang theory. Now, not all galaxies follow this pattern. Here is the spectrum of our Sun, and here is the spectrum of a distant galaxy. Now, if you notice, the pattern is different. The dark lines have moved towards the blue end, and we call this a blue shift. And whenever we see a blue shift, that means something is coming towards us. So it may well be that this galaxy, the gravitational attraction of another galaxy is making it move inwards or move back towards us, rather than moving away from us. So there are some galaxies that do show a blue shift, but the vast majority show a red shift, which means that everything is moving away from us and the universe is expanding. So Sir Edwin Hubble approached this very scientifically, and he took all of his data and plotted it on a graph. And you can see the graph here. The x-axis is distance of the galaxy from the Earth, and the y-axis is the velocity of the galaxy relative to the Earth, where he took his measurements from. And you can see that they cover a pretty good straight line. And what he concluded from that was that the further a galaxy is, the faster it's moving. And if you go back in time, then everything must have been together in one place, which is evidence for the Big Bang theory. And you might notice this anomaly here, these set of results. And these results are from a cluster of galaxies called the Virgo cluster. And gravity is having an effect on these, and it's pulling all of the galaxies in towards each other. So a number of these galaxies didn't follow the pattern exactly, but he identified them as being in a cluster of galaxies. Now, as this is physics, it shouldn't come as a surprise to you that we bring some maths in, and sometimes the maths can give us a deeper understanding. And if we look at the light from the sun and compare it to light from a distant galaxy, as we've talked about, the light from the distant galaxy shows a red shift. And if we look at one line in particular, this line here, when we look at that same light from a distant galaxy, the line has moved over here and it's shifted by this amount. So the wavelength, the length of this dark line, wavelength of this dark line is increased by a certain amount, and we use a mathematical symbol for that, delta lambda, and lambda is the symbol we use for wavelength, and delta lambda, which is this lambda symbol here, is the change in wavelength. So basically, you could be given a question, you're given the original wavelength and you would have to work out the change in wavelength. And what that then allows us to do is, if we know the change in wavelength, which is here, and we divide it by the original wavelength, which is there, that's equal to the speed of light, the speed of galaxy v divided by the speed of light. So if we know the change in wavelength and we know the original wavelength and we know the speed of light, then that will allow us to work out the speed or the velocity of the galaxy. So it's a really useful equation to have, and this is what Sir Edwin Hubble used to work out the velocity or the speed of different galaxies. And that concludes the first bit of evidence for the Big Bang Theory, and we will move on to the second bit of evidence in the next video. So what do you need to do now? So we've covered this first piece of evidence for the Big Bang Theory, and I want you to click on the links in the assignment and attempt the 2 multi-choice quizzes. That will help you to go over this video and go over the PowerPoint and reinforce the basic knowledge, and then answer questions 1 to 3 on pages 26 and 27, and then when you've done those, move on to the past paper questions on pages 30 to 42 of the booklet. And if you can get through that and understand it, you've got a strong grasp of this section of work. Thank you very much.